Hello friends, how are you? I hope you all are good and doing well. In this video lecture, I am going to discuss with you a very important topic on nuclear and particle physics. The topic is nuclear isomerism and explanation of this with the help of single particle cell model. Friends, this topic is very important as this is asked in different competitive examination from the last 2005 to till now. It is important from the competitive point of view as well as the academic point of view because this is also given in the CSIR UGC-NET syllabus as well as the UPSC-IAS mains optional physics paper. So friends, please stay tuned throughout whole of the videos because this is going to be very interesting and valuable for you. I will show you the syllabus. Friends, as you can see, this is the CSIR UGC NET for JRF and lecturership syllabus of physical sciences. And in the part B, advanced, there is a topic under the nuclear and particle physics, where it has been asked evidence of cell structure and single particle cell model, its validity and limitations. So, friends, in this video lecture, we are going to cover this topic evidence of cell structure, single particle cell model, its validity and limitation, and the nuclear isomerism, its explanation with the help of single particle cell model. So, firstly, we understand the phenomena of nuclear isomerism and what is nuclear isomer. So, friends, a nuclear isomer is a metastable state of an atomic nucleus in which one or more nucleons occupy higher energy levels than in the ground state of the same nucleus. Metastable describes nuclei whose excited states have half-lives 100 to 1000 times longer than the half-lives of the excited nuclear states that decay with a prompt half-life, generally the order of 10 to the power minus 12 seconds. The term metastable is usually restricted to isomers with half-lives of the order of 10 to the power minus 9 seconds or longer than that. That means usually 10 to the power minus 8 seconds. Friends, earlier it was common to assign a separate isotope to a particular lifetime. Thus, if two half-lives were observed in a given sample, it was assumed that they were due to two different isotopes, each decaying with a particular half-life time. For example, let us consider the decay of thorium into the protactinium. In this decay process, there is emission of beta-decay and Protactinium was found to decay by emission of beta particles of two different half-life times, that is 1.18 minute and another with 6.66 hour. So, in the 1921, German physicist Otto Hahn showed that these two half-lives of beta decay are not due to two different isotopes, but because of two different energy states, excited energy states of the same nucleus. Such long-lived excited states of the same nucleus are called the isomeric states or nuclear isomers and or nuclear isomers, and this phenomena is known as the nuclear isomerism. Friends, you can see that having studied the decay of uranium, German physicist Otto Hahn noticed that uranium-238 emits alpha particle to create thorium-234. It can then undergo beta decay to form either the ground state of Protactinium-234 or an excited state of Protactinium-234. Both these states of Protactinium can then beta decay to form uranium-234. These two states of Protactinium proved that isomers exist. This is the picture of German physicist Otto Hahn with his colleague Lise Meitner at the Kaiser Wilhelm Institute in Berlin in 1913. Friends, in last year, in April 1921, we, that means world, celebrated the century of the invention of the nuclear isomer. Friends, now we will discuss about the nuclear cell model. Under this nuclear cell model, we will discuss about the evidence of the nuclear cell model and the main assumptions of the nuclear cell model, magic numbers, and so you can see here in this diagram that is number of protons versus number of neutrons, and this black line is the stability curve that is highly stable, that is for the highly stable nuclei, and you can see that these numbers 2, 8, 20, 28, 50, 82, and 126, these are very important numbers which have many significance in the physics. So we will discuss all these things. You know, the large binding energy means high stability of the nuclei. The nuclei that have the number 2, 8, 20, 28, 50, 82, and 126 neutrons or protons are more abundant in the nature than the other nuclei of similar mass numbers. This suggests that their structures are highly stable. The nucleons means number of neutrons and number of protons. Thus, in nuclear physics, a magic number is a number of nucleons such that they are arranged into complete cells within the atomic nucleus. As a result, atomic nuclei with a magic number of protons or neutrons are much more stable than other nuclei. These seven most widely recognized magic numbers. Other magic numbers are also have been recognized. Those are 114, 122, 124, and 164 for protons, as well as 184, 196, 236, and 318 for neutrons. Now we will show by the example of the selenium 58 140 that how these nucleons are more stable. So you can see that this nucleus contains 82 neutron and 58 protons. Binding energy of this nucleus can be calculated as 58 into mass of proton plus 82 into mass of neutron minus mass of the nucleus. That is equal to 1172.75 million electron volt. Therefore, the binding energy per nucleon can be written as B by A is equal to 1172.75 million electron volt divided by 140. That comes out equal to 8.377 million electron volt, and that is nearly equal to 8.38 million electron volt. So friends, we see that the binding energy of the nucleus selenium 140 is higher by the average amount of 4 million electron volt compared to its neighbors. The cell model of the nucleus is an attempt to account for the existence of magic numbers and certain other nuclear properties in terms of nucleon behavior in a common force field. Friends, now we will study about the evidences that led to cell model. So there are few evidences that led to the cell model assumptions. One of those evidences is first, after the careful study of the binding energy per nucleon B by A versus atomic mass number, it is revealed that sudden kinks or discontinuities have been found to occur whenever either the neutron number or the proton number or both take the values 2, 8, 20, 28, 50, 82, and 126. That is helium, oxygen, SR-38, 88, and lead. You know that after every chain reaction, lead is used to be the last product in the radioactive reactions. Second evidence is stability is related to high natural abundance. Pronounced peaks are found at helium, oxygen, calcium, tin, selenium, lead, confirming the existence of the magic numbers. I will show this with the help of the diagram for the natural abundance versus the atomic number. Here in this picture, you can see that the relative abundance of the elements versus atomic number for helium and oxygen, there is pronounced peaks relative to the other elements that shows the stability confirming the existence of magic numbers. Third evidence that led to the cell model conception is the relative stability of different elements is also indicated by the number of stable isotopes or isotones per element. That means more number of isotopes for an element indicates that the more stable the element is. For example, tin 50 120 has 10 stable isotopes, which is the maximum number of stable isotopes in all the elements. Comparing this with the indium 49 and antimony 51, which have only two stable isotopes each. Thus, the number of isotopes also indicates the completion of fulf- fulfilling of the cell that led to the assumption of cell model. The fourth evidence is the doubly magic number. I will tell you about the doubly magic number. Friends, the nuclei which have neutron number and proton number each equal to one of the magic numbers are called doubly magic and are especially stable against the radioactive decay. That means in the doubly magic element, number of neutrons and number of protons both are any magic numbers. So in that case, both nucleons used to have a magic numbers. That's why these are called doubly magic numbers. The known doubly magic numbers, the known doubly magic isotopes are helium-4, helium-10, oxygen-16, calcium-40, and calcium-48, nickel-48, nickel-56, and so on. The heaviest stable nucleus, lead, also have the doubly magic number. In this case, number of proton, that means Z, is equal to 82 and number of neutron is equal to 126. That means in the case of lead, both the number of proton and number of neutron are magic numbers. This indicates the stability of the nuclei. Friends, as you know, the final product of all of the three of the radioactive series is lead, and the most abundant lead isotope is this. The final product of Neptunium series is bismuth, which has number of neutron 126. That is also a magic number. Therefore, in general, the doubly magic nuclei such as helium-2, oxygen-8, calcium-20, lead-126 are particularly tight bound nuclei and are doubly magic nuclei. Further, the evidence that led to the assumption of cell model is number fifth. When the known isomers are plotted against proton numbers or neutron numbers, we get groupings. Just below the magic numbers, these groupings are called island of isomerism. I will show you this with the help of the diagram. Friends, you can see in this diagram that before each magic numbers, when we plot the isomers against the nucleons, there is a groupings. These groupings are known as the island of isomerism. There is a sharp break at each of these magic numbers, and that signals a disappearance of isomerism. When a cell is completely filled, isomerism does not occur again till the next cell is about half full. So, this is also an evidence which led to the assumption of cell model. Now next evidence is the nuclear electric quadrupole moment Qi becomes practically zero at magic numbers since the quadrupole moment vanishes for complete spherical symmetry. That means Qi will be zero only for the complete spherical symmetry of the cell, and that occurs for the even nuclei number. That is, if n and p are even, then we can have only the spherical symmetry, and in that case, the net spin will be zero. That means Qi will be very low for nuclides having closed cells. Friends, now we will discuss about the main assumptions of the single particle cell model. So let's start the single particle cell model assumptions. Single particle cell model is the simplest nuclear model obtained by applying the quantum mechanics. The first assumption for the single particle model is for odd nuclei, the nuclear properties like spin, parity, and moments are determined by the unpaired nucleon alone. This effectively reduces the many nucleon problem into a single particle problem. That means only the odd number nucleon is going to contribute for the spin, parity, and moments. The assumption number two. It is assumed that each nucleon experiences a central attractive force, which can be ascribed to the average effect of the remaining nucleons in the nucleus. Assumption number three. In this central field, each nucleon is assumed to move in a cell in a manner analogous to atomic electrons. This implies that each nucleon can describe several revolutions around the force center before being disturbed by collisions with other nucleons. That is, the mean free path between the collisions among the nucleons is much larger than the nucleus diameter. Assumption number four, the cell model assumes that the interaction among nucleons to be weak, which is true according to the Pauli exclusion principle. Friends, now I am going to tell you about the assumption number five for the cell model. Maria Geoffert Mayer add to a potential dependent on position only strong spin orbit coupling between nucleons, which give the JJ coupling of nucleons in the nucleus. Maria G. Mayer was a German-born American theoretical physicist and a Nobel laureate in physics for proposing the nuclear cell model of the atomic nucleus. She was the second woman to win a Nobel Prize in physics, and the first woman was the Marie Curie. So Maria G. Mayer proposed a strong spin orbit coupling between nucleons, and spin orbit coupling helps in satisfying the magic numbers. The interaction energy in terms of spin orbit coupling can be given by W is equal to minus lambda divided by C square M 1 by R du by dr into S dot L, where Lambda is the strength parameter, and that is a dimensionless quantity. M is the reduced nucleon mass, and U is the potential, and R is the radial distance. And S is the spin vector, and L is the orbital angular momentum vector. So, in this way, Maria G. Mayer proved the nuclear cell model as a strong tool to explain the magic numbers existence. Friends, these are the things that I wanted to discuss with you in this video lecture. I hope that you enjoyed this video lecture and will be fruitful for you regarding your competitive examinations and academic exams also. Friends, if you have not subscribed this Sai Academy channel, please subscribe it because we used to bring the very important topic on physics relevant to your academic as well as the competitive examination. And also press the bell icon so that you get the notification of the upcoming videos and you could not miss the important lectures. Thank you, friends.